Is there enough time to be aware? As you can imagine, this talk will be about time. It'll be about how do we use time and how do we use time together. So before we go over a roadmap, let's take a brief trip on what we know about time to just refresh ourselves. We know that you can't really have a point in time. Time is more so an interval, a session. We know this because with statistics, if you take a point in time, then there's infinite points under that curve, and thus, whenever you try to do any sorts of probability, it does not work. You need to actually have a range or an interval, and the same thing is with time. What else do we know about time? Let's talk Stephen Wolfram and computation irreducibility. If no one is familiar with what we figured out, with what Stephen has figured out in this last year or two with Wolfram Alpha, his research into causality has mathematically proven that there is a point in the future that we cannot look past if we're looking at a bifurcation in chaos theory. And so there really is a range that we can actually observe in the future. And this we're bound by it. This is also very interesting. And of course, Einstein said there is no time, there's space-time. So, space-time and tide wait for no man. And I've never been on a calendar, but I've been on a calendar, but I've never been on space-time. And that one actually doesn't quite work there. That one actually does work there. And this reminds me, with Joe Armstrong was always preaching, do not break the laws of physics. If you want to program correctly, don't do it. Don't share memory because you're breaking the speed of light in that instance with the Dirac light cone. The last three talks that I gave, and Maxim is helping me out with, by showing some pictures out there. If you want to do the one with the 112, it's got the talk names. The first talk I gave was WX Erlang and representational faithfulness, where we talked about the conceptual statement number 8. Conceptual statement number 8. That one. Go back. Here we go. Focus is in. This conceptual statement is how the world harmonizes its accounting standards. So both financial accounting standards and international financial accounting standards use this model. Next one, if you want to go to we'll come back to that in a bit. So I wanted to show you all that. The two prongs of it were reliability and representational faithfulness. What we're going to see is that reliability is, relevance and representational faithfulness. Relevance is a lot like time. It was composed of predictive value and confirmatory value. The second talk I gave was on the major takeaway from it was this idea of composing in style, where when you compose something in a way, you're actually adhering yourself to some sort of continuous manifold. Like think of fire, for instance. Fire is kind of a manifold. So when you start to map manifolds onto manifolds and you want to actually have a continuous function, homotopy type theory, you actually want to make sure that the function is continuous throughout those manifolds. But this isn't to say that things can't be discrete. Do you want to put up the 2x2 so that people can see the one that looks like a cross? Yeah. Discrete systems, okay, and we'll get to the horizontal axis in a bit. Discrete systems are much more like light going through different density mediums in which their refraction occurs, where you actually have, in a way, three parties. You have the light, you have the medium, and you have the thing observing the light in the medium. And usually there's a triad in discrete systems. So hopefully we can build to that by the end of the talk and show and set the stage for the next time we actually visit this, that seems to be a conceptual framework that does hold. And in the last talk I gave, which was WX Erlang, it was your Erlang graphics. We started to look at the digraph module in Erlang and how we can fix it to actually bring us closer into writing categories and category theory. How can we evolve this to be smaller, more independent parts that can actually glue together is where we're going with that. And so hopefully with those tools, we're going to begin to stack to the future. The talk, I have to apologize because the talk I was supposed to give, I said I would give next, was Alchemists of the Erlang program. which was going to go over, well, still is going to go over the history of the Erlangen program, which was all of essentially the early parts of category theory. Now, the early category theorists actually got together around in the late 1800s, and they started to set the stage for homotopy type theory and category theory. And it's, the thing's called Erlangen program, so I'm surprised no one's actually even just accidentally looked at it yet. Because that is essentially where we're trying to go with this next series of talks. This being the first. Is this idea of harmonization. Perhaps we can bring the accounting conceptual framework into Erlang and actually begin to harmonize the many languages together by actually looking at our type systems and trying to find what are the generic patterns in between them. So with that said, the reason I had to give this talk was because of my sponsor, the DevXDAO, which is a Swiss not-for-profit. We give grants to programmers who want to build open source projects that further decentralization. So if any of you have an open source project in your mind, please go look at the DevXDAO sponsor. We want to give you money so that you can actually do your project. DevXDAO.com. So that last talk of digraphs, the category of a digraph is interesting. It has two nodes. One of them being your edges and one of them being your vertices, and it has two arrows pointing from your edge to your vertice, because there's the vertice that, the edge has a vertice that it came from, and it has a vertice that it's going to. That's what defines an edge. And because category theory is made of digraphs, in a way, it is kind of the reflexive property of digraphs in themselves, which is, it's very curious, if you will. So, yeah, let's put that one down, because I do want to expand on that in the next talk. For now, we do need to cover some ground on the open source open systems interconnection framework, which I hope over half the audience has it memorized. So yeah, you got it, yeah. But it's a physical data link network transport session presentation application. Now, this model in itself has the 7 layers. We can use this as a philosophical tool. Hold on. Well, first off, this is the stack. If we're talking a stack to the future, if you're talking a full stack programmer, this is your framework. This is what we're talking about. Can you connect the application layer down through a set of protocols to the physical layer, which is the wires? Now, the physical layer is what is defined. Your data link layer ends up being your names and your namespace. The network layer ends up being, when you really get into it, it has this element of categorical priority, which is and whenever you try to create a system, or whenever you try to define a category, you're bound by priority, you're bound by sequence. You actually can't escape this idea of sequence in itself. Without using more of a physical layer construct, but that's a different layer. So in the network layer itself, you have categorical priority. Your transport layer ends up being your buffer to buffer, basically pouring water in between cups back and forth, where your computer has many registers in it. Your session layer, like I mentioned earlier, ends up being this idea of time, but not a point in time, an interval of time, hence why sessions. Lambda, if you will. There's a start and a close to your lambda. In Erlang, it's so expressive because you can actually voice these lambdas in so many different ways. Even the idea of a gen server where it has an initiation and a termination in itself is kind of a session layered lambda. It's no other language really has that construct. It's a superpower of ours. And it's no surprise that it is one of our main generic behaviors that exists in all of the OTP framework. Your presentation layer ends up being just a state. So we think statefulness and mutability. So the presentation layer always has this kind of element of mutability to it. And this is why you have cryptography here in this layer, because you can just mix things up and you can demix things in the presentation layer. And eventually the application layer in itself is this idea of functional transformation. Now, if we're in this framework, what is I have to make a sales pitch here for programming languages, where I believe where we're going is a Erlang stack on the top of the OSI framework and a Rust stack on the bottom part of the framework, where for the first time we have, sorry C, but for the first time we have 2 levels of fault tolerance, where we can be building fault tolerance at the Erlang level and have Rust, as we call our NIFs, have our back, so that if something fails at a low level, we actually can correct it at that level as well. This is our stack. Now, let's come back to the center. Now, let's move on here to what does stacking the future look like? Now, the center of the OSI framework is your transport layer. Yeah, if you want to just remind people. Now, the transport layer comes down to reliable propagation. I'm going to say that again because it's really important. It's about reliable propagation. If your buffers start to misfire, then you're going to lose data and some bad things are going to happen. Erlang likes a network that has reliable propagation. Fault tolerance helps when the network begins to break down. I'll say that again because it's really important. You don't control your networks a lot of the time. And so when your network begins to break down, something that's not your fault, you need to be able to protect yourself from it. And that is why Erlang is such a fantastic language. It's because it gives us the power to protect ourselves from things outside of ourselves. Now, and this idea of reliability, if you don't mind me going back to the OSI, to the conceptual statement number 8, representational faithfulness used to be known as reliability until about 2009, and then they changed the name to faithful representation. Now, reliability in itself ends up being this idea that we talked about with manifolds earlier, about pathing between two manifolds. Because with representational faithfulness, it's defined as the phenomenon that is attempting to be purported accurately purports the phenomenon. So you're trying to get some sort of continuous function, or at least some sort of non-broken discrete function to make sure that you have completeness, which was right underneath representational faithfulness in that framework. So this idea of pathing, equivalence is equivalent to equality, is a statement made by the category theorists quite often, and the homotopy type theorist as well. Equivalence is equivalent to equality plays into this idea. It means nothing if you don't have a reliable propagation of a wave between 2 points. So we need that fault tolerance. And we have to talk about something difficult here that people tend to glaze over with Erlang, which is death. It's not a fun topic to talk about. Our processes die so that we don't have to. Just the way the prefrontal cortex kind of works, where our paths die so that we don't. We can protect ourselves against the outside forces of the world by actually running simulations or paths to try to find some end. And this is very important because this gives a quality to Erlang that no other language really has. It lets us strive to get, and we should be striving together, and that's what this community. I believe I can speak for everyone here, and I hope that I don't offend anybody, but by saying that we all love Erlang because we like to strive, and Erlang helps us strive, and helps us strive better than any other damn tool out there. And so when we have teams of people who program Erlang, who's going to clean up after ourselves when we die? We have to take this question seriously. It was one of the questions that plagued Joe Armstrong whenever I was hanging out with him. He was always worried how we're going to remember the world's history. And it's up to us, because we need to strive and we need to figure out how to remember the world's history. The two most difficult things in programming are what to name things and what to cache. And I believe the burden falls on us. So we need to strive together. And let me rephrase that. How are we going to clean up after us as a civilization? And this programming language and the stack can give us the tools to do so. So where do we need to go, and where are we today? Where do we need to go? This is a book, A Pattern Language, which was really prevalent when I first came into the community about 5 or 6 years ago. Garrett was talking about it. It was all the rage, but I didn't really understand it because of, quite appropriately, the book that preceded this was A Timeless Way of, The Timeless Way, which appropriate. This is the second book where they describe a certain type of timeless way. You can actually put up the really complicated one that breaks this 15 parts of the timeless way. I'm sure that's an interesting thing that people might want to screenshot. And what I didn't get as a beginner, and I want to tell to people who are interested in this book, is that when they're talking about a pattern, they're not talking about a pattern matching pattern. That's what I thought it was at first. They're talking about an Erlang generic behavior. They talk about this idea of if we can abstract generic behaviors together, protocols, then we can build into the future together. We can make living spaces, as they call them, that allow us to speak this, the pattern without a name, I think is, I hope I'm not butchering that. I'll read a quick excerpt. It is shown there that towns and buildings will not be able to become alive unless they are made by all the people in society, us. And unless these people share a common pattern language, which we have generic patterns, within which to make these buildings, or programs, and our smart houses, by the way, just that's coming. And guess what's gonna run that? What do you want running your smart house? And unless the common pattern language is alive itself, which we have the ability to create a pattern language that is alive. Other languages do not have this. The burden is on us. So yes, and you can see if you look at that pattern again, the generic versus the 2x2. I am going to make a line here from this idea of internal generic inheritance going to the, wait for it to focus, back up a little bit, buddy. Going to the external specific idea. And we have a very nice 2x2 here that we can use to measure this, okay? That kind of shows internal and external versus what is continuous. Remember, space-time, it's a manifold, it's continuous, okay? Time really isn't intangible. Time is extremely physical. It's very, very tangible. Versus this idea of discreteness, which is we need a third party to actually break apart the two patterns that it's seeing to actually interpret some sort of outcome, which is this. And it usually ends up being like reflection, but this is a conversation for another day. And so what do we have? Oh, where are we today? And I want to bring it back because there's another tool that we just got in our arsenal, which is blockchains, which ends up being very much like this idea of concurrent going outwards. Like if you have a system and you're going to be sending a message out from your concurrent system, this is where blockchain becomes very, very, very useful. It's this idea that can connect, and the difficulty here is connecting the computer time to the human time to the global time. That is going to be our challenge within this, as blockchain is upon us. And when we're talking about blockchain, if you ever need to describe it to somebody, remember, it's not like it's a general ledger, but it's really a group of computers that are actually getting consensus talking to each other. Like, tell people what it is physically. Like, it's a bunch of computers that talk and carry a shared state forward through time. And so yes, if you're interested in, so the DevX DAO just funded me to build something called Casper. It is the programming bindings to the Casper blockchain in Erlang. Hopefully during the talk for the last 5 minutes, I'm going to be editing it and adding some slides in here. It will have been going through and showing everybody how to use this API. It basically is an SDK, a development kit for the Casper blockchain, so that all the Erlangers can then interact with a blockchain very easily and have some documentation on there, so that it's easy, as SDKs do make things. I encourage everyone to remember to strive, and I encourage everyone to remember that our future hasn't been written yet. Okay, so we have to make it a good one.